Hello everyone, and thanks for attending this webinar. My name is Estelle Asta, and I'm glad to start this seminar about EMC systems immunity against ESD. As an introduction, let's define what is EMC immunity and what it means for you when you design an electronic printed circuit board. EMC stands for electromagnetic compatibility. EMC immunity is the ability for an equipment to properly operate in its electromagnetic environment by limiting the reception of electromagnetic energy that may cause physical damages. Electrostatic discharge, called ESD, fall into this category. ESD can be either conducted under the form of a transient voltage, but it can be also radiated due to its fast rising time, generating harmonics powerful enough to generate erratic behavior of your application by coupling with other signals. It means that ESD is a threat against which your printed circuit boards must be protected. Here is an example of EMC immunity. At ST Microelectronics, we ensure that our printed circuit boards embed ESD protections for all connectors that may be subjected to electrostatic discharges. As you can see, there are many ESD protection references in this board. So for HWPCB designer, it can be a tricky job to select the correct ESD protection according to the connector. So let's review today what ESD protection at system level means and what are the different standards behind. Then we'll explain you the selection steps for the ESD protection component, and finally, we will detail the layout guidelines to properly fit the ESD protection in your design. In this first part, I would like to remind you how ESD is generated in everyday life and why we should care about it in our electronic applications. ESD is a result of static electricity discharges. Static electricity is a collection of electrically charged particles on the surface of a material. Various materials have a tendency of either giving up electrons and gaining positive charges, or attracting electrons and gaining negative charges. The list of these materials in the order of how much they become positive or negative is called the triboelectric series. A discharge of tens of kilovolts may occur, and the arc that appears is called ESD. Here are some examples of voltage levels. For instance, walking across a carpet is the worst case, generating up to 35 kilovolts. Discharging that amount into integrated circuit is not without risk. Electrostatic discharge will cause potential failure on the integrated circuits of your PCB. These failures are called electrical overstress, or EOS, resulting in silicon melting, oxide punch-through, junction damage, metallization damage, or degradation, affecting the long-term reliability of your electronic system. A survey from the EOS Industry Council showed that 30% of customer claims are due to ESD or EOS. And furthermore, the miniaturization of the components is increasing the integrated circuit sensitivity to ESD. Here is a graph showing power supply voltage, VDD, and breakdown voltage, VBD, of various semiconductor technologies used for integrated circuits. The breakdown voltage, VBD, and the power supply line, VDD, are decreasing year after year. The ESD design window, that is the difference between VBD and VDD, is also decreasing drastically from 8-volt margin in 1999 to only 2-volt margin in nowadays technologies. This illustrates that ESD sensitivity is increasing in integrated circuits and that it is necessary to protect these sensitive ICs with a specific external ESD protection. Now there are different standards for ESD and two major cases. The first one on the left side is related to component level ESD. This is to ensure the manufacturability of integrated circuits. These standards reproduce ESD during manufacturing processes, which means the ESD risk is mitigated by using specific equipment in a controlled environment for manufacturing. For instance, technicians can wear anti-static shoes and they are deionizer to avoid air charging. Each person or equipment must be connected to the ground in order to allow a discharge path. The related standards are HBM, Human Body Model, that simulates ESD due to discharge from human being, MM, Machine Model, that simulates the machine ESD discharging through a device to ground. And finally, CDM, Charge Device Model, that simulates ESD due to mechanical device handling the ESD protection according to the standard concerns any integrated circuits. It is called on-chip ESD protection. The second case on the right side is related to system-level ESD, and this is a case that occurs in our everyday life. The IEC 61-4-2 standard simulates a whole system that may be subjected to ESD. For instance, working on a carpet with a vinyl suit could generate, on a dry environment, several tens of kilovolts of electrostatic discharges as presented in the introduction. In this case, the only way to manage an ESD event is to add a dedicated ESD protection mounting on the PCB and placed in the critical discharge path. The automotive standard, ISO 10605, is also part of system-level ESD. What are the main differences between HBM, Human Body Model, and IEC standards? From our experience, people do not often understand the difference between these two standards. On the left side, the electrical circuits modelize the equivalent ESD waveform associated to each standard. The IEC standard is modelized by a larger capacitance discharge, 150 picofarad for IEC, against 100 picofarad for HBM. And this capacitance is discharged through a much lower resistor, 330 ohms for IEC compared to 1.5 kilo ohm for HBM. On the right side, we compare the energy carried by the current waveform of these two standards. For the 8 kV IEC, the current is in red here, and with same 8 kV voltage, HBM current is in green. For 2 kV HBM, that is the most common level specified for integrated circuits, we obtain the blue curve. The energy of ESD that corresponds to the surface below the curve is much lower than for 2 kV HBM compared to 8 kV IEC 61000-4-2. As a consequence, IEC 61-4-2 carries more energy than HBM. This is why integrated circuits exposed to ESD and specified with HBM will still require an external ESD protection rated per the IEC standard. While you may wonder why integrated circuits do not feature system-level ESD protection. So let's try to figure out what will be the size of the system-level ESD protection integrated in an IC. Here we show two integrated circuit protection layouts using the same scale thanks to pad surface. On the right side, you can see the size of an IEC protection 8 kV, which is much bigger than the size of the 2 kV HBM protection at the left. This means integrating 8 kV IEC protection is not cost-effective in expensive advanced MOS technologies. This is why the system-level ESD protection is kept external using specific silicon technologies. Now let's review the IEC 61-4-2 standard. This is a system-level standard. It is not related to component, so it applies to a complete application with its enclosure. This standard defines 4 stress levels and 4 levels of results. The most severe level is level 4 with 8 kV contact and 15 kV air applied. The test result is rated A when the device under test performs normally without any disturbances. At ST Microelectronics, all ESD protection components comply or exceed this level 4. For automotive applications, the ISO 10605 standard applies. It is more severe than IEC standard because of a higher capacitance used for discharge, 330 picofarad instead of 150 picofarad for IEC, a higher number of discharges, 50 instead of 10 for IEC, a higher frequency to apply the ESD pulse to the components, and finally, a higher level of apply voltage up to 25 kV at contact discharge instead of 8 kV for IEC. On top of specific semiconductor reliability testing, automotive ESD protection are usually priced higher than ESD protections used in consumer or industrial applications. So now let's review how to select the right ESD protection component for your application.
Thank you, Estelle. Now, we will present on this section the key parameters of an ESD protection. How these parameters can impact your system performance, and at the end, I will give you some basic advices to select the right ESD protection component. Here are the key electrical symbols and abbreviations we will use so that you can get familiar with the vocabulary. Let's review in detail each parameter. VRM stands for maximum reverse voltage. It corresponds to the maximum voltage of the protected line or normal operating condition. It is associated to IRM, the leakage current of the ESD protection. This current is very low to not impact the system consumption. It is typically much lower than 100 nanoamps. ESD protection starts to conduct at breakdown voltage, or VBR. The static voltage is usually measured at 1 milliamp. It can be used to validate that the ESD protection is well mounted on the printed circuit board. During an ESD event, the surge current is flowing into the ESD protection. The maximum current that can flow into the ESD protection is called peak pulse current. The associated voltage is called clamping voltage, VCL. The clamping voltage is the remaining voltage measured after ESD protection. The lower the clamping voltage, the better the protection efficiency. The last key parameter is line capacitance. In the frequency domain, an ESD protection can be modelized with a diode with a junction capacitance. This capacitance can impact the signal line integrity as any extra capacitor placed on a signal line. An ESD protection can be unidirectional, like IV curve on the left, or bidirectional, like IV curve on the right. Here is the principle of transient voltage suppressor, also called TVS. Keep in mind that ESD protection is a subclass of TVS. Let's consider an electrical signal in blue. This is a voltage curve function of time without TVS. Unfortunately, at a voltage higher than destruction value, the system fails. To avoid this system failure, a protection is required. A TVS is then used to clamp the voltage in pink and then to protect the system. At VBR, or breakdown voltage, the TVS starts to conduct in green. The current flows into the TVS and the resulting voltage is a clamping voltage. The forward voltage, VF of the TVS, clamps the negative signal for unidirectional protection. Another key parameter is the leakage current of the TVS itself. The IRM defined at maximum reverse DC voltage on normal operating condition, VRM. In case of signal polarity which is both positive and negative, the TVS must be bidirectional. In bidirectional TVS, the voltage thresholds are usually the same in both directions. The ESD protection must protect the IC or the application, but must not impact the application in normal operation. For example, the parasitic capacitance of ESD protection devices must be low enough to allow HDMI 1.4 gigabit per second high-speed signals to be transmitted without degradation. A high parasitic capacitance of ESD protection devices would increase too much the signal rise and fall time and prevent good communications. In one word, if the capacitance is too high, the rise and fall time will be too high, and then the signal integrity will be impacted. To guarantee the digital signal integrity, the following equation is used with FC cutoff frequency and TR rise time. The ESD protection cutoff frequency must be lower than the application operating frequency. A lower capacitance allows a larger bandwidth and a better signal integrity. In our example, we can see that the orange curve representing 5 picofarad capacitance is too high for the HDMI 1.4 gigabit per second signal. We can also see that a 1 picofarad ESD protection capacitance is okay. Indeed, eye diagram or eye pattern measurement is a tool to characterize transmission quality. In digital communications, the eye diagram is used to visualize how waveforms used to send multiple bits of data can potentially lead to errors in the interpretation of those bits. An eye diagram is produced by repeatedly sampling a digital signal on oscilloscope's vertical axis while triggering the horizontal sweep with the data rates. Acceptable signals are often defined with the use of a mask, here in blue. The mask usually consists of a polygon in the middle of the eye and rectangles above and below the eye. If the measured traces cross the mask boundaries, the signal quality is considered unacceptable. high-speed buses, standards like HDMI, USB, and so on, often specify eye diagram masks. If measured traces cross the mask boundaries, the signal quality is considered unacceptable. On datasheet of ESD protection for high-speed buses, eye diagrams are reported for various standards. In this example, USB 3.1 Gen 2 at 10 gigabit per second per channel is reported. The measurement is performed on a line without ESD protection on left and with ESD protection on right. We can visualize there is no impact of the HSP 053-4M4 on the USB 3.1 at 10 gigabit per channel signal. The signal integrity is respected. Another key parameter for high-speed buses is the time domain reflectometer impedance, or TDR impedance. It is specified on standards where long cables are used, such as HBM, but it is not mentioned on any USB standard. The TDR impedance is measured thanks to an incident step with well-controlled rise time that is reflected on the unmatched load. Both signals are measured with the high bandwidth and high sample rate oscilloscope, and the post-calculation extracts the impedance of the load. It is also reported on datasheet of ESD protection for high-speed buses according to the standard constraints. As example, a line with and without HSP 053.4M5 is characterized according to HDMI 2.0b TDR specification. For analog signal, S21 parameter on dB is also reported on datasheet. It corresponds to signal attenuation due to the protection. As example, SDA RF02 1BU2CK can be used to protect antennas. It has a negligible impact on major frequencies used for wireless telecommunications. Now, let's focus on ESD protection quality. The key parameter is the ESD response to an electrostatic discharge of 8000 volts. As example, ESD 051 1BF4 temporal response is presented. There are two noticeable values. The first is the peak voltage at the beginning of the response. It's a low energy peak due to the duration of 2 nanoseconds. It was formed corresponding loosely to a CDM ESD event. For ESD 051 1BF4, it's 23 volts. The second is the clamping voltage, defined as 30 nanoseconds. It's 11 volts for the ESD 051 1BF4. It's much more energetic due to the duration. This temporal response at 8 kV is usually reported on datasheet because it corresponds to the IEC 61000-4-2 level 4. To perform ESD analysis, transmission line pulse is used. A square current pulse of 100 nanoseconds is injected into the protection. The remaining voltage is then measured between 70% and 90% of the incident pulse duration. For ESD 051 1BF4 with 16 amps incident current, the TLP voltage is 10.5 volt. It's about the clamping voltage measured with 8 kV ESC 61000-4-2. With several pulses at various incident currents, it is possible to make a TLP IV curve. As example, ESD 051-1BF4 TLP IV curve is presented. On same graphic, a TLP IV curve of microcontroller input is plotted in blue. 3 voltages are noticeable for MCU. The first one is a working voltage, 3.3 volt. The second one is the absolute maximum rating of this input, 5.5 volt. The third one is the MCU destruction, 12.5 volt. TLP destruction voltage of this microcontroller is higher than AMR because TLP duration is only 100 nanoseconds, while AMR is continuous. This graphic shows that current coming from ESD event is shared between MCU internal protection and ESD 051 1BF4. When the sum of current into the ESD 051 1BF4 and MCU is higher than 16 amp, the system can resist to 8 kV IEC 61000-4-2. This is a system efficient ESD design methodology or SEED methodology. The approach shows the current repetition between external ESD protection and the protected pin. Instead of standard ESD protection, green TLP IV curve, snapback ESD protection can be used red TLP IV curve. Snapback protections present lower clamping voltage than standard protection thanks to the snapback effect that lowers the clamping once the protection has turned on. At 16 amp, ESD V5 1BF4 presents a clamping voltage nearly 2 volts lower than ESD 051 1BF4. But the protected line DC voltage, if present, must be lower than holding voltage of the snapback ESD protection. Indeed, if DC voltage is higher than holding voltage and if ESD event is present, the protection will turn on and the current coming from the DC voltage source will flow continuously into the protection. The protection will then be latched. If no DC voltage or no DC voltage higher than holding voltage, there is no latch risk. To select the right ESD protection, 3 parameters must be validated. The ESD protection must be transparent for the application. To do so, the protection capacitance must be in line with the application bandwidth if analog or data rate if digital. These curves are reported on datasheet. The ESD protection must be efficient when ESD event is present. TLP IV curves are present on ESD datasheet, but there is no TLP information on the circuit to be protected. To select the protection with a good clamping, it is recommended to select an ESD protection with a VRM just above the maximum line voltage. To avoid snapback protection latched up once turned on, holding voltage must be higher than DC line voltage to grant a good system integration. All these information are available on the application notes, Fundamentals of ESD Protection at System level on st.com.
Thank you, Matthew. Protection requirements are becoming more and more well-known and are often defined by rules or standards, as we described so far. To satisfy these requirements, there is in the majority of cases a standard solution or a dedicated protection product. However, knowledge of the disturbances and the use of a suitable protection devices are not sufficient in themselves to solve the problem. In many applications, the correct design of the PCB layout is essential for success. Let's have a look on a particular example for the PCB layout consideration. Let's try to understand why it is very important to have the application PCB layout under control for a good ESD robustness. The circuit presented in this figure shows the classic approach for the protection placement in the application circuit. Here, the protection device is located between the connector and the IC device we want to protect. What is not visible in the first view is the fact that during the ESD disturbance, the PCB track impedance starts to play an important role. High current and the trace impedance causes unwanted overvoltage at the protected IC pins. Depending on the PCB technology, the PCB track impedance of around 1 nanohenry per its millimeter of length is introduced. This problem is specifically important for the PCB track parts colored in red in our figure. Let's consider for the next exercise that the single PCB track inductance L is 5 nanohenry. When an ESD disturbance occurs on the PCB track from the connector on the left side, the protection device clamps the surge at its maximum clamping voltage, and thus we expect it protects our sensitive IC. It's not really true in this particular PCB layout, because during this clamping action, there is a high current going through the protection device and also through the PCB tracks around it. This phenomenon introduces a voltage on the PCB tracks equal to the track impedance and the current change. If we consider 5 nanohenry inductances and the current change of 37.5 amps per nanosecond, the resulting VIC, visible by the protected IC pin, is simply a sum of the protection device clamping voltage and the voltage introduced on the PCB track. In our case, the VIC is hundreds of volts, and apparently these levels can be still crucial for the protected IC. So what should we do? The solution is simple. Our application PCB tracks must be under control. In particular, we have to shorten the PCB tracks and route them through the protection device pins as visible in the figure. Connections to the ground must be also short, and specifically the vias to the ground planes must be as close as possible to the protection device and to the protected IC ground pins to limit the parasitic inductances. In detail view, the PCB tracks inductance stay out from the risky area and does not contribute to the potential overvoltage visible by the protected IC pins during the ESD event. With the optimized PCB layout, the VIC on the protected IC pin is the wanted clamping voltage of the protection device. It is also recommended that the protection device is located as close as possible to the disturbance source. In our example, close to the connector. For more detailed information on the PCB layout recommendations for your ESD robust application PCB design, you can consult our application note called AN1751. Now, let's have a look through several application examples showing recommended protection devices for particular application cases, along with the recommended PCB layouts. The application core product is usually a microcontroller. It features many peripherals which are in the final application naturally exposed to the surrounding environment. As an example, we all know many different communication buses like USB, RS-232, Ethernet, with their connectors accessible to outside environment. We have also audio connectors, slots for the memory cards, or just a simple push button in our applications. All of these peripherals should be protected in an ESD robust design. Let's go now through several concrete examples. First example is the USB connector, which should be equipped with a protection device which is capable to protect the microcontroller pins against ESD, but also at the same time the protection device should not introduce high capacitance to the communication lines in order to stay compliant to the USB I diagram. USB LC6 protection device can do the job, and you can find the recommended schematic and PCB layout at our reference designs for STM32L4 microcontrollers. Similar for RS-232. In this case, the RS-232 transceiver is the most exposed application IC outside the application through the connector, and also in this case, as it was mentioned for the USB connectivity, there are two main functions or needs for the protection device required. The first one is the ESD protection functionality itself. The second key requirement is again the capacitance of the protection devices itself introduced to the communication line, which must be low to keep the RS-232 protocol compliant. Also in this case, you can find recommended schematic and layout in our STM32L4 reference board resources. Last example we selected are the user buttons and consequently protection of the microcontroller GPIO inputs. Although these mechanical buttons, being part of the application, are exposed outside to the environment. The buttons are not made from a conductive material. Nevertheless, they are still highly sensitive to the ESD, and they are also stressed during the IEC certification test. Beside the ESD robustness level, such protection device requirement is usually also on the size of the package to keep the PCB space occupation small. The small package size is often a general customer requirement for any protection device. Now let's have a closer look on concrete application boards. The first mentioned already at the beginning of our webinar is showing the ESD protections suitable for our STM32MP1 microprocessor. As you may see, all exposed connectors are equipped with ESD protections. In addition to the connectors, we have also added protections to other sensitive areas, such as the user input buttons and the SD card slot. The protections added to this board ensure system-level protection in compliance with the previously mentioned ESD standard IEC 61000-4-2. Any electronic board must be protected. This second example is showing a 3D printer control board. On this board, both input power lines of 12 volt and 24 volt are protected against surge, means according to IEC 61000-4-5, as you can see on the left side of the PCB layout. In addition, there are several ESD protection devices on the board. ESDA 5V3L is used for the user button. EMIF 06 is protecting the SD card slot, including also the EMI filter. And finally, the USB LC6 protection devices are used for all 3 USB connectors populated on the PCB. We have mentioned some application notes already in our webinar. Here is the recommended list of our documents you may check to make your application design robust and optimized from the beginning, means already at the schematic level. We also invite you to watch our additional video about ESD protection, explaining why and how you can protect your application ICs. For example, the microcontrollers in an efficient way. ST Protection Finder is the software application available for Android and iOS that allows you to explore the ST's protection portfolio. You can easily define the device that best fits your application using the parametric or series search engine. You can also find your product thanks to the efficient part number search engine. To find the right device for your application, it is just enough to explore and fill entries through 4 particular steps. You just need to open the ST Protection Finder application on your phone, entering the product family you want to search in, for example, ESD protection. In the second step, you narrow the parameters needed for your application, and you select from the preselected protection devices the best fitting product for your needs. Web links to the datasheet and the online documentation are also reachable through this app. Thank you for listening. This is the end of our webinar, and we can proceed to the Q&A session now.